In this video, we're going to consider the exponential nature of radioactive decay. And we're going to come up with a couple of equations that model it. We're going to have a look at two tests that we can do to check as to whether our data is showing exponential change. And we're going to return to an idea that you've met at GCSE around half-life. So firstly, radioactive decay is random. In other words, you cannot predict when a particular nucleus is going to decay. You cannot say that it's going to decay in 2 minutes or 4 minutes. All you can do is say that there's a probability of it decaying. It's also spontaneous. So all those external factors that we can often change to influence the rate of reaction, for example, pressure or temperature, do not change the rate of radioactive decay. However, just because it's random doesn't mean we cannot model it. And the examples of flicking a coin and rolling the dice are a good analogy here. So if you flick a coin enough times, you will observe the 50-50 probability between getting a head and a tail. And similarly with rolling a dice, if you roll that dice enough times, you see that 1 in 6 probability of landing on a particular face. So we can model random behavior, and that's what we're going to have a look at now. To do that, we need a couple of definitions. And the first one is activity. So the activity of a source tells you the number of decays per second. And we're not going to distinguish between whether they're alpha, beta minus or beta plus decays. It's simply the number of decays per second. And the unit that we could associate that with is the becquerel, after one of the pioneers in this field, Henry Becquerel. So if you've got a substance with an activity of 100 becquerel, it's telling you that every second there are 100 decays. So if that particular nuclei decayed by alpha, you get 100 alpha particles every second. Or similarly, for something that decayed with positron decay, you get 100 beta plus particles per second. Now, activity is directly related to the number of undecayed nuclei that you've got. So if you double the number of undecayed nuclei, you're going to double the activity. You're going to double the number of decays that you observe every second. So activity is directly proportional to the number of undecayed nuclei. And that's what the letter N represents in this instance. So that's the relationship then. We now need to turn this into a useful formula. Activity is minus lambda n. Lambda is the constant of proportionality, and that is what we're going to call the decay constant. And it's a measure of the probability that a nucleus will decay in a certain amount of time. So a substance with a high decay constant or a large value for decay constant is going to show us a high probability of decay. In other words, it's going to lead to a more active substance. We are going to observe more decays per second. The minus sign is in there to show us that we are getting a decreasing number of undecayed nuclei over time. Okay, that number is decreasing over time. So activity measured in becquerels is equal to minus lambda n. In terms of the units for the decay constant, they are time to the minus 1. So it could be seconds to the minus 1, hours to the minus 1, years to the minus 1. It kind of depends on the substance as to the value of lambda as to which unit that you use. And that makes sense because if we rearrange the equation, lambda is minus A over n. So that is just decays. It's just a number per second. So activity is per second, and that's just a number. Okay. The decay constant only depends on that particular nuclide. In other words, it's specific to each nuclide. So uranium-238 has a particular value of lambda, and that's different to let's say thorium-234. Okay, and it is not dependent on the decay mechanism. There's not necessarily a correlation between the value of lambda and whether it's alpha, beta, or gamma decay, and it's certainly not dependent on any of those external conditions that we've talked about so far. So in other words, activity being minus lambda n is really a measure of the rate of change of those undecayed nuclei. And now we begin to see something that we've met before when we looked at capacitors. We've seen it before when we've looked at the amplitude decaying for oscillators undergoing simple harmonic motion. The rate of change of undecayed nuclei is related to the number of undecayed nuclei. Okay, so the rate at which that is changing is all dependent on the number of undecayed nuclei. Okay, so we could say that dn by dt is proportional to n. Whenever we've seen this before, it's always led to exponential change, hasn't it? So when we were talking about capacitors, the rate of charge or discharge on a capacitor was directly proportional to the charge present on the plates at that moment in time. When we were talking about the amplitude of a simple harmonic motion oscillator, the rate at which that amplitude was changing was dependent on the amplitude at that point in time. And so it's no great surprise then that if we follow that derivation that you've got on the screen, which you don't need to be able to do, but for you mathematicians, it's nice to see where that's come from. We are able to solve this first order differential. So dn by dt is proportional to n, and come up with a solution in this form. And this is a really useful formula for when you need to know the number of undecayed nuclei at some point later in time. Okay. Now, because A is minus lambda n, in other words, A is directly proportional to n, we can have this alternative form of the equation. I'm not quite sure what my pen and my board are doing at this moment in time. There we go. So activity is also varying exponentially. Okay, there is an exponential decrease in the activity of a radioactive source. So just kind of checking that this makes sense and this works. So when time is 0, e to the minus lambda t takes on the value of 1, because e to the minus 0 is 1, and therefore our equation becomes n is n naught. In other words, at the beginning, when we start measuring time, the number of undecayed nuclei is equal to n naught, where n naught is the initial number of undecayed nuclei. Okay, so a new equation, but following a familiar form that we've seen on several other occasions. So in terms of using the equation, it's just a straightforward substitution of numbers. So in the example that you've got there, how many nuclei will remain after a time of 3 hours? The answer that you get is 3.62. So is it 3 or is it 4? Yeah, it's somewhere in between those two numbers. We'll never be able to be certain as to whether that final decay has happened or not. Just be careful when you're doing questions like this as to whether you're being asked for the number that will remain or the number that have decayed. Okay, so the number that have decayed is the difference between your starting number and the number that remains. So just be a little bit careful of that. Now, whenever we've met exponential change before, we've been able to test for it graphically and also by the constant ratio test. So you've got the justification again for the constant ratio test. which we've seen before. So let's just kind of remind ourselves of this. So if we're plotting activity against time, we know we're going to get that characteristic exponential shape. So we pick a starting activity and we read off a value for time, and then we might choose to halve it. So we look at A over 2, and we kind of consider the time period that it took for that to happen. We then look at halving again. So in other words, activity by 4, and we look at that time period, and so on and so on. And what we should find is, as long as we change the activity by the same fraction or the same ratio, that took place in the same amount of time. Or in other words, in a fixed interval of time, the number of undecayed nuclei or the activity of that source will change by a constant ratio. So this is great if we've already got data plotted and we just want a relatively quick and straightforward test. Okay. We can also plot a logarithmic graph. And if we do that and the data is exponential, then that should generate a straight line graph. So in terms of the proof for that, it's very similar to the proof that we've considered when we've looked at this with capacitors and simple harmonic motion. So the first thing that we do is we take logs of both sides. And we recognize that in this bracket here, we've got two things multiplied together. And whenever we've got the log of A and B multiplied together, it's equivalent to the log of A plus the log of B. So we can write the log of n equaling the log of n naught. And then we've got the log of that exponential function. So that's going to remove the exponential function. But don't forget, it's minus lambda t. And so we get that term. So if we plot a graph of the log of n against time, we are expecting that to be a straight line graph. So there is what is plotted on the y-axis, time is on the x-axis. We're expecting a negative gradient, which equals the decay constant. It's a constant, so we're expecting a straight line, and there is the y-intercept. So we can work back to the number of undecayed nuclei at the start. Okay, that's n naught by looking at the y-intercept. And we can also work out from the gradient the decay constant. Okay, so there are two tests for whether something is exponential or not applied to radioactivity. Now, why might we want to work out the probability, the decay constant, from the gradient? Because it links into half-life. Now, you are already familiar with this from GCSE. It's the time taken for half the undecayed nuclei to decay. I guess we could also say it's the time taken for the activity of a substance to halve. Okay, because A is directly proportional to N. So we're going to define half-life then as the amount of time it takes for N to be the starting number of undecayed nuclei to halve. Okay, and we're going to use that little half subscript against T to denote that we're not just talking about any amount of time now. It's the half-life that we're talking about. Okay, so N is N naught e to the minus lambda t. Okay, and N is now the starting number of undecayed nuclei divided by 2 when the time is t to half. Okay, at which point I can cancel out my n naughts. And I've got half on the left-hand side, and then I've got that exponential term on the right. So I'm going to take the log of both sides now. The log of a half is equal to the log of that exponential function. So that's going to cancel the exponential function, and I'm going to get minus t half. Log of a half is a bit like the log of a divided by b, isn't it? Okay, so we've got the log of a minus the log of b is the relationship there. So we've got the log of 1 minus the log of 2 equals lambda t half. Put this into your calculator. The log of 1 is 0. We've then got a minus sign there, which can cancel with that minus sign there. So log 2 is lambda t half. There's all kinds of craziness happening on my screen here. I'm not quite sure why it wants to do all this stuff. Rearrange it. T half is log 2 over lambda. Okay, put log 2 into your calculator. 0.693 over lambda. Okay, so in other words, there's that inverse relationship between the decay constant and half-life. The bigger the value of decay constant, the bigger the probability of decay, and therefore the rate of decay is going to be more rapid, and therefore the half-life is going to be shorter. So that makes sense, doesn't it? That's entirely consistent. Okay, so in the same way that the decay constant depends only on the nuclide, not on the decay mechanism, whether it's alpha, beta, gamma, not on any external conditions, that has to be true, doesn't it, for half-life? Okay, it's completely independent of all of those things. So in terms of the units are really derived based upon the units for the decay constant. So decay constant is kind of time to the -1. So that's going to give us units of time for half-life. As I said to you, it depends on the units that you've used for lambda as to the units that you've got for half-life. Okay, so those are all of your equations that you need to know. There are 2 tests that we've gone through for determining whether data is exponential or not, and that is our modelling for exponential decay.